I'm going to be talking about fatty acid synthesis or lipogenesis. The name is telling you what we're doing. We're synthesizing a fatty acid. This is happening in the fed state. Synthesis pathways happen in the fed state. So when we eat in excess, we'll eat more carbs than we need at the moment. We're going to turn them into fatty acids, and then those will soon be turned into triacylglycerols. But for now, we're just focusing on the fatty acid synthesis part of it. So glucose is turned into pyruvate. Pyruvate is turned into acetyl-CoA using pyruvate dehydrogenase, or oxaloacetate using pyruvate carboxylase. We know carboxylase enzymes use B7 and dehydrogenase mostly use B3. So acetyl-CoA and oxaloacetate will be combined to form citrate in the TCA cycle. Citrate synthase is what makes citrate. So citrate's going to move out of the mitochondria into the cytosol to do the rest. Citrate lyase is going to cut citrate back into acetyl-CoA and oxaloacetate. Acetyl-CoA carboxylase is the rate-limiting enzyme. It's using B7 because it's a carboxylase. And it's using HCO3 to add another carbon into this reaction to turn a 2-carbon molecule into a 3-carbon molecule. So it's turning, ACC is turning acetyl-CoA into malonyl-CoA. And fatty acid synthase is going to conduct 4 reactions. They're all going to be focused around turning malonyl-CoA into palmitic acid. These are 4 reactions that are opposite of what we saw in beta oxidation. In beta oxidation, that was breaking down a fatty acid into acetyl-CoA. Here, we're doing the opposite. We're building a fatty acid. So before, we remembered OHOC because it was oxidation, hydration, oxidation, cleavage. Now this is CRDR. Condensation, reduction, dehydration, reduction. So it's the opposite of those 4 reactions in beta oxidation. Fatty acid synthase uses B3 and B5. So essentially what we're doing here is we're producing palmitic acid. That's a saturated fatty acid. It's the most abundant fatty acid in our body, and it's 16 carbons. So each time we do this reaction, we take 2 acetyl-CoAs, add 7 malonyl-CoAs with, so malonyl-CoA is a 3-carbon molecule, but we only use 2 carbons from it. So we do 7 malonyl-CoAs, 1 acetyl-CoA, and we get palmitic acid, which is 16 carbons. So that's where we're getting our carbons. Once palmitic acid is made, it's going to be turned, it's going to be combined with glycerol to make a tag. Over here, I forgot to mention that the oxaloacetate's going to turn into malate, and malate's going to turn into pyruvate. Malate dehydrogenase is doing this reaction, and malic enzyme is doing this reaction. Malic enzyme is producing NADPH, which is used in these reactions. So just know one of the places we get NADPH is from the malic enzyme reaction that takes place during fatty acid synthesis. So that's why I wrote it here. NADPH comes from not only the pentose phosphate pathway, but the malic enzyme reaction taking place here. Fatty acid synthesis occurs when, like I said at the beginning of this video, when we eat too much glucose for our need right now. So we turn glucose into fatty acids, and then we put those fatty acids with glycerol into a tag to be stored in our adipose tissue. So most of our organs make fatty acids, most importantly adipose tissue, liver, lungs, brain, kidney, mammary glands. Stimulators of fatty acid synthesis are glucose, obviously, because that's what's starting this reaction, and insulin, because insulin's released in the fed state when there is glucose in the blood. Acetyl-CoA will stimulate this pathway because we're adding malonyl-CoAs onto acetyl-CoA to form palmitic acid. So malonyl-CoA will stimulate it too. Citrate will stimulate this pathway because we're forming it initially to get acetyl-CoA. NADPH stimulates this pathway because it's being used in these reduction reactions. A fat-free diet will stimulate fatty acid synthesis because if we're not getting fats from our diet, we need to make some. So this is why we do this. Inhibitors of fatty acid synthesis are glucagon, because this is a synthesis pathway. Synthesis pathways occur when we're in the fed state. So glucagon's going to inhibit this pathway because that means we are in fasting or starvation. Palmitic acid will inhibit this pathway because that's the product. Whatever you're producing, typically, if it's high, it's going to inhibit this pathway because this pathway is designed to make palmitic acid. If we have it, we don't need to be doing this pathway. And then a high-fat diet will inhibit this pathway because if we are eating fat, we don't need to make it. We're just getting it from our diet. The way that we elongate fatty acids is by sending palmitic acid to the smooth endoplasmic reticulum and adding malonyl-CoA onto it until we get the desired length of fatty acid that we need. Desaturation of fatty acids. So a saturated fatty acid means it's saturated with hydrogens and there's no double bonds. So unsaturated means we stuck in a double bond. And when we unsaturate or desaturate a molecule, we need three things. I remembered it as cytochrome B450, O2, and NADH. And humans are incapable of, I guess we don't have enzymes to add double bonds past carbon 9. Omega-3 and omega-6 can do that for us. That's why we need to eat them. And just remember that linolenic acid is omega-3. The two ends can turn into 3 if you put them together sideways. I don't know if that makes sense. And then linoleic is 6. Or you can remember as linolenic is longer, and it goes with 3, which is shorter, and linoleic is a shorter word, and it goes with the longer omega-6. I hope that made sense.